Okay, hello everyone, and thank you for joining us in another AM Smart webinar, webinar number 8. And as you notice, this webinar is going to be about the elastocaloric topic, very interesting topic about the smart materials and specifically shape memory alloys. And there's been some colleagues all around the world working on this nice topic. Today, we have Professor Paul Motzki from University Saarland in Germany. He is hosting this meeting. Also, Paul has experience in this topic, University Saarland, and also his colleagues. They have been working on this topic for a long time. And now I'm going to give the floor to him and let him to introduce two excellent speakers that we have today for this specific webinar. That's all from my side. Thank you for joining us, and please, Paul, go ahead.
Thank you, Mershad, very much for the invitation and the chance to host this very exciting webinar here today. Also looking forward at the Elastocalorics conference that we established 2 years ago, and we are gonna host once again in 2 weeks. I'm very excited that I was able to find 2 excellent speakers for today. And before I introduce the first one and we jump right in the topic, let me, for everyone in here, just quickly share, and this is my advertisement block. It only takes like 30 seconds. From May 13th to 15th, we are hosting the Elastocalorics conference once again in Saarbrücken. Registration will be open until the day of the conference. Also, we are accepting last-minute poster submissions if you're interested to hold a pitch talk and present a poster. And we've already have around 90 participants today as we are speaking. So it's going to be a great conference, also including both speakers today will be present on site in 2 weeks in Saarbrücken. So that was my little advertisement block. And then let me jump into the introduction of our first speaker. I think in the announcement, we had it the other way around, but because of technical issues, I would love to introduce the first speaker today, Julie Slaughter. Julie, she's a scientist at Ames National Laboratory working on replacing gaseous refrigerants in air conditioners and refrigerators with solid-state caloric materials. Her areas of expertise are in multi-physics modeling of active materials, magnetics, caloric materials, and system design and magnetostriction. She holds a PhD in engineering mechanics, Master of Science in Mechanical Engineering, and a Bachelor of Science of Mechanical Engineering. So it's my pleasure to listen to the talk. I'm very exciting. Julie, the stage is yours.
Okay, thank you, Paul, for the nice introduction, and thank you for inviting me to talk today. I really appreciate that. So I'm going to focus my talk on some of the work we've done here on low-force elastocaloric devices and their applications. So just a little bit of background why we're interested. Really, there's a lot of potential applications and advantages, and this really goes everything from very cold, hydrogen liquefaction temperatures up to industrial heat pumping. And, just a few data points here. Conventional hydrogen liquefaction consumes 35% of the liquid hydrogen energy. So that's really an issue that needs to be addressed. And in the US, over 20% of households struggle to pay their energy bills. So if we can come up with a lower cost, more efficient way of cooling homes and heating homes, that's really a big bonus for that. And then refrigerants are, harmful to the environment, and really about 10 to 20% installed refrigerants leak annually. So that's kind of some of the motivation for why we're interested in this. And just to kind of throw this out there at the beginning, elastocalorics are really fairly new, but there have been some exciting advancements recently. Kilowatt scale demonstrations for cooling. There have been high power and large temperature spans. This is kind of a multi-mode operation. And there's, heat-driven SMA, heat-driven cooling has also been demonstrated. So there's just a lot, low force. And then, my colleague who'll be talking later has demonstrated Jaka Tušek, he demonstrated a compression-based generator that had a very high specific cooling power. And so these are just some of the exciting things I've seen recently in the field. So let's talk about this for. So what is elastocaloric cooling? And see if I can get a pointer here. Oops, there we go. So this would be the active regenerator cycle. So if we start at the top, we're at an ambient temperature, and then you apply a field. Now I've got magnetic field, electric field, and elastic fields here. So this is kind of generic to any caloric cooling or heating technology. So then you apply a field, the material heats up, and then you transfer that heat to an external heat exchanger. Then your material is back to that ambient temperature. Then when you remove the field, it cools off. So now you're cooler than you started. So and then you absorb heat from a load, an external load, another heat exchanger there. So you go through that cycle, and you can build up a temperature span larger than the material itself. So if the material itself, changes, this delta T is 5 degrees Kelvin, you can actually generate a temperature span 3 to 4 times that quite easily. So 15 to 20 Kelvin. And that's a reasonable temperature span for refrigeration and air conditioning and heating. So that's really kind of a basic description of what active elastocaloric regeneration is. So then I want to talk a little bit about the technical challenges. So the materials, what you really need is a large response in a low driving field. That's really important to be able to get a large temperature change when you apply this field in the material. That helps a lot with the building devices. The second thing you need is tunable temperatures. I showed the previous slide where we went from everywhere from liquid hydrogen liquefaction up to industrial heat pumping. So you really want to be able to tune the temperature. It needs to be inexpensive, non-toxic, and then it needs to have chemical and mechanical stability. So for elastocalorics, mechanical stability really is mostly talking about fatigue, because that is the main failure mode for some of the elastocaloric materials. So once you have the materials, the next thing is you have to have an active regenerator. So if you look at this step, it needs to be a good heat exchanger. So the material needs to be, it's not just a solid and you're transferring heat in and out of that. That wouldn't be very efficient. So you have to have, in some cases, parallel plates, wires. Packed particle beds are for magnetocaloric, but something that you can easily flow fluid through and exchange the heat. So that's really what's important for active regenerators. So how do you get the right geometry for that to be able to do that efficiently? And the next thing is, what is your field source? So this is typically, for any caloric system, the largest and heaviest component that you're going to have. So what applies the stress field, what applies the magnetic field, what applies the electric field. So you really want to exist, there's existing technologies, linear motors, rotary motors, whatever. You want to be able to match the fields that you need in the material with the existing technologies. So that's really how you get to a system, is that. And then finally, devices and systems. In the end, what you need is better thermal performance than compressors at equal or smaller cost, size, and mass. You have to have some kind of performance or cost advantage, or there will be no transition to elastocaloric cooling. So given that bit of background, I'm going to talk a little bit about some of the systems and challenges. So this is just a nice graph that shows the difference between tension and compression in nitinol. So, you'd like to operate in compression because that is better for fatigue. This is nitinol, this is nickel titanium, which is by far the most common material used for elastocaloric systems. So in compression, it has lower hysteresis, but requires very high stresses, 700 megapascals, which is really pretty extreme. Temperature needs lower stresses, but it has larger hysteresis and is prone to fatigue failure. So we're kind of looking at how do we achieve a compact, efficient device with the materials we have today. So I want to start first by talking about how do you, that big heavy piece of the system, the actuator, how do you apply the fields? So just start and look, a very basic comparison is what is the energy density of the elastocaloric material, what does it require, and then what actuators are available, what do we have available for actuators. So if you look at this, it's a little bit busy, but what we have is stress and strain, and these lines are the constant energy density. So in the transparent ovals, these are different families of elastocaloric materials. And so you can see we have ferroelectrics, we have nickel-based, copper-based, iron, palladium, natural rubber, and then, there's nickel titanium with pre-strain. I've got an example later that will talk about that. And then for actuator materials, so we have piezoelectrics and moving coils. They have typically a fairly low energy density. Magnetostrictions, magnetic shape memory alloys, and pneumatics kind of come in this middle category. And then in the high category, shape memory alloys. So actually nickel titanium, heat-driven actuator material is actually a really good match for nickel titanium elastocaloric materials for energy density. That's not surprising. And then hydraulics kind of fall on that line, but with larger strain and lower stresses. So there's a few options. None of them are ideal. The two that kind of fall in the best category here, shape memory alloys and hydraulics, are not very efficient. And then, magnetic shape memory alloys are not commercially available. Pneumatics, again, not very efficient. So we need another metric to look at here. So we're going to look at next power density, and this brings frequency into the equation. And this kind of takes advantage of the fact that you can operate indirectly on the elastocaloric material at the system level, gearboxes, lever arms, things like that. So, this brings rotary motors into the actuation. So you're not just working with something that, directly stretches or compresses the material. So here, rotary motors are actually a really good fit because you can change the frequency with the gearbox. That makes them and they're ubiquitous. So that's kind of where we're leaning to drive this, is how do you figure out how to use rotary motors? You don't want to use magnetostriction or piezoelectric. There's not a good way to translate the frequency into power density. So they've all got kind of this upward slope. So if you can operate at higher frequencies, they have higher power densities, but doesn't really match what you can do with elastocalorics, because you're really limited to less than 10 hertz if you're acting in kind of this active regenerator mode. So that's just kind of a couple different ways to look at how you design the system and how you match actuators. So really, when you kind of approach the device design, you really want, the materials inherently have a high power density. And so you really want the actuator power density to match that as best it can, so that you can kind of minimize the size of the system. And then another important point is that energy recovery and pre-strain can help minimize the size of the driver. And what we mean by this is when one elastocaloric element is loading, another one is unloading, so you're recovering that mechanical energy. Second point I want to look at here is at this initial stage of developing new technology, we need to see what materials are out there, what can we use that's off the shelf. And so super elastic nickel titanium materials are commercially available in several different forms: wires, sheets, tubes. There's probably even billets, but this is really tailored for medical applications. So right now it's expensive, but what I want to point out here is there is a growing interest in tailoring materials for heat pump applications. So really, I think the cost will come down, because this, if it takes off in heating and cooling, that's an enormous market that will, in fact, just completely overwhelm medical applications. So I think there is interest from companies out there for that. So now we're going to get into a little more details about some of the work we've done at Ames Lab. So we've really focused on this, how do we reduce the forces needed and match the elastocaloric element with the actuators that are available. So one of the first things we did is look at, how can we reduce the force? Because, actuators, typically, we can produce more displacement than force in a lot of this actuation material. So what we've done is we've taken this active nickel titanium element and combined it with a passive structure so that when we bend this, and in bending takes a lot less force, we actually get tension on this upper element in this 4-point bend configuration, and we had used half the force to do that. So we took that concept and kind of said, well, how do we get some of this energy recovery and make this a more efficient device? So what we've done here is we've made this a two-sided structure where we have a bias tension on both elements, and then we obviously this, you can't compress an element like that, but here you can increase and decrease tension. So we have always a hot side and a cold side of this. So you actually now have multiple elements, so you can have more of a continuous operation of the system. So that's kind of where we started with some of our ideas on that. And we looked at this this concept and said, okay, are we achieving, high power density? How is this at the system level? And we did, rotary motors had the power density and the range we needed. So really what I've got here in this table is looking at the motor volume, or whatever the actuator is, to the active material volume. So if you look at competing technologies like magnetocalorics, typically the magnets and all the magnetic components make up it's about a 3 or 5 to 1 ratio of magnetic material to active material. And so we want to at least be at that same level for elastocalorics in order to really start to be a commercially viable system. So what we looked at in this double-sided structure is, how much material volume, and we ignored a lot of the structure, but we did say, okay, what is the active material volume to a motor ratio? And we achieved actually a very, very good result of just under 4 to 1. Looking at some of the other systems, one used, one was a heat-driven system, the other used terphenol D, a magnetostrictive. So you can see that we're actually in really good shape. There's other systems out there that are probably much better. This was a fairly old result, so I'm sure everything has improved by this time. But that's really where we're aiming at, is to get to that same type of ratio for the material volume to the active material volume. And our goal ultimately is to get high power density. So how many watts of cooling or heating can you get from a system per gram of the system, and not just at the material level, active material. So now I want to talk specifically about one of the projects we have here at Ames Lab. And this is elastocaloric cooling for military vehicles. So what I want to point out here is the military has a strong pain point here. Their current refrigerants are being phased out, but they use the leading alternative for vehicle air conditioning has a risk of sustained burning, which, I guess they've decided is okay for passenger vehicles, but that's not acceptable for military applications. And then they're also concerned about other refrigerant blends that break down into harmful chemicals such as PFAS. So this is kind of their motivation for why they want something different. So our project was selected for funding under this, and we're evaluating elastocaloric cooling, and we have 3 main goals for this. One is to optimize nitinol alloys for cooling. And our really main goal there is to reduce the stress strain hysteresis and fatigue while still maximizing caloric performance. Second goal is to demonstrate this active regeneration and see, can we meet the temperature span requirements and efficiency requirements. And then third is really to demonstrate a 500 watt system. So that's where we are. We are in the middle of this, working on all three efforts right now. So a little bit of what we've done for the materials. We're partnering with a couple different companies that we're working with optimizing the materials. ATI and GRAL are the 2 companies. And the material we selected already has low inclusions and good fatigue. So we want to even reduce the reduce the hysteresis and improve the fatigue. So the first thing we tried was some high temperature heat treatments that reduced the grain size. So this did improve fatigue, but did not impact hysteresis. And so we looked at kind of some different options. There are low temperature heat treatments. We were able to shift the austenite finish temperature by plus and minus 10 degrees, but it didn't have any effect on hysteresis. But what this might allow us to do is to tune the materials to better perform over a wider temperature band. So that's still a good result. I just want to point out in this curve, you look at the purple here and the orange. This is the same material, and it's just 2 different days in the lab. So the temperature of that material is so close to room temperature that it's extremely sensitive to any minor changes. So just want to point that out. If you're using it for cooling, you want that austenite finish temperature to be below the temperature you want to operate at. So this would not be suitable for room temperature cooling, but it is suitable for higher temperature applications. So just something to keep in mind. We are going to start moving to ternary and quaternary alloys to reduce the hysteresis and fatigue. So that's really where we are with our materials effort on that. Then we're going to move to the active regenerator design concept. So this is a little complicated, but what we've done is taken our bending tension concept, where we have this passive beam in blue. We're applying a bending moment. This is a fixed end. And then we have a stack of plates. So instead of just having one single plate on each side, we're actually putting tension on a whole entire stack of plates. And what this does is a couple things for us. One, it increases the amount of active material we have in our structure. But secondly, it makes a nice parallel plate heat exchanger. So this is a good structure for heat exchange. So we're really, and to address the fatigue issue, we're really operating at a bias strain and then operating a fairly low oscillating strain around that. So we have a strain of 1.4% that's a bias, and then we're plus or minus 1% on that. And that gives us a temperature change in the material of about, I think, 5 to 6 degrees Kelvin. And that's sufficient to get our ultimate goal of this. And we did, in our final element, it said we've got about 1/3 of the force that would be needed for direct tension of, already we reduced it by 1/3. So it's 67% of what we would use for that. So we did some active regenerator modeling. Our target for a single regenerator is 125 watts at 0 span and 25 watts at 25K span. So the plate's thickness we have is 200 micron thick, and we have a 50% porosity in that, so they're spaced 200 microns apart. So with 100 grams of nickel titanium, we can exceed that target performance that we're looking for. You can see this line in both cases. This is versus at different frequencies. This is a different utilization, and that's utilization is related to how much fluid you're flowing in each of these cycles. So in either case, we can exceed the performance that we're looking at with these 1D models. So that's great. Now we need to really have, what does the mechanical design look like? So what we ended up with is we have 2 stacks of material on either side, and that was limited by what material we had available to us. And we are driving this at this end. We have a rotary joint here that applies tension without any moment to the nitinol. And so that's really just kind of the mechanical details. The flow manifold is a bit of a challenge because you have to flow fluid in and out here. We're not using air. We're actually using a water-based heat transfer fluid because that has a lot higher heat capacity and a better match for the nitinol. So that is the complicated design we have come up with and built. The mechanical characterization looked really good. We had our finite element model in our experiment. But what we did find is a lot of these mechanical connections are kind of coming loose as we do this. So there's some engineering problems we need to fix here. Let's see if the movie will actually work. So this is the thing in action. You can see right here, there's a mechanical joint opening up and loosening. And if you look, there's a drip of water underneath. So right now we're struggling with sealing the fluid connections and having a little bit of mechanical problems. But that's where we are today. So we're in the midst of fixing those issues right now and finding the seals and making sure that we can get this to work. So it's a challenge, but we're getting there. But in the meantime, we're kind of looking at that next level. And what does the system look like? So it's going to have multiples of these regenerators. They're probably not going to look exactly the same, but you know, this is a kind of cartoon. So the final size of 500 watts. If we reach our 125 watt goal, we'll require 4 regenerators. So the next thing we looked at is how do we achieve energy recovery with that? Because if you drive all 4 of those at once, you're just going to increase the amount of torque you need by a factor of 4. Well, then you can do a little bit better than that if you have, you know, say a single cam with 3 lobes, you can reduce that by half. But you're still not getting true energy recovery. So we're looking at now is driving each of those regenerators independently. And this, when we do this, you can actually, so if you look at this plot here, so in the flat areas, this is where it's either all the way in or all the way out, you know, because you're moving up and down. We'll call it up and down. So you get these. This is the torque required. So this would be a single regenerator, and it goes up to about 175 Newton meters. So if we run all 4 at once, and we can actually match the timing so that when one is loading, another one is unloading, we can reduce that to about 100 Newton meters. So we can actually demonstrate, and this is just, you know, models at this point, but show that we are getting some energy recovery from the system. I think this would be improved if you had more regenerators and, you know, improve the timing even more. So that's kind of where we're starting with that. I did want to just, not going to go into any details on this, but we are working with a small company that's using bending, which is an even lower force. I mean, direct bending of the nitinol. And this, you know, you still can get a, you know, with a 6%, you know, 6 times reduction in force, you can get the same temperature change in the material. So we're partnering with a small company that's developing some cooling systems for U.S. military based on that concept. So there are some good, exciting things. And then I want to just bring this in as kind of a technology. How does it compare to other technologies out there? So this was taken from a recent paper that we did on magnetocalorics. And so you can see the green and blue areas here are what is the power density? And this is how much cooling power per kilogram at the system level. So this was taking all the magnetic components into account. And this gray area is where compressors are today. So how many watts of cooling do you get per kilogram of the compressor? I think it ignored the refrigerant in that. So this gray area is really where you find compressors. Magnetocalorics is starting to get there, especially at the low end of things. And so I said, okay, let's take these 2 theoretical devices, the one single plate one, and then our 500 watt system. If they perform as expected, you know, because that material power density is already so much higher, it looks very promising. So we need to get some hardware built and show that for real, but you know, we're pretty happy with where that started. So, and then just kind of wrapping up here, outlook and future directions. So there's a lot of recent advances that show promise for real world applications, but I think there's still improvements in the materials, there's improvements in regenerators, there's a lot of different issues, you know, a lot of different approaches out there. Some people are using compression on tubes and you know, different configurations for there. So really there's a lot of options and a lot of good directions moving out there. So really, I want to point out that if we're looking for applications, let's start with high value applications where they have a pain point, particularly like our military applications. And then the second one is, where is it competitive with performance, size, and cost? So I'm going to leave it with that. Acknowledge my colleagues at Ames Lab and the U.S. Department of Energy and Department of Defense for our funding. And thank you for your attention.
Thank you very much, Julie, for this really nice presentation. And I would like to open it for questions, as Mershad already written in the chat. Please write your questions right into the chat. And here's already the first question. I will read it to you. How do elastocaloric systems move heat effectively, and what makes the heat exchangers, in parentheses, regenerators, work well over time?
Okay, that's a great question, and I don't have, maybe I can go back to the, so what makes them good heat exchangers? Let's go here. So because it's a solid metal, you need it to be in a porous form. So this is why when we have, multiple plates, so you now have a parallel plated heat exchanger. So what you do is you're flowing a fluid. So what I haven't shown here is this is fluid flow through that porous structure. And then there is a heat exchanger, an external heat exchanger that exchanges the heat with the environment. So that it's kind of a two-step process. One, you're absorbing the heat from the active material, and then you're expelling that heat through a secondary heat exchanger to the environment, if that makes sense. I don't know if that answered the question or not.
Yes.
So there's second part. Okay, good. Thank you.
Very good. Are there any other questions? Thank you so much for the presentation. May I know, how do you fabricate the manifold for the heat transfer fluid?
We are currently 3D printing that picture. Yes, so this flow manifold right now is a 3D printed part. So it has very intricate internal passages to keep nice laminar flow at the flow rates we're working with.
Okay, I also have one question. You mentioned the strains you're operating at, and the 5 to 6 Kelvin. What is the expected cycles of why you chose this plus minus 1% of effective strain?
A little bit. There's been a few publications out there. Actually, one by my colleague who'll be speaking soon, Jaka, Tušek, that looked at pre-strain and that the effect on fatigue life. And so I think this was kind of in the range where you could get a decent fatigue life with that. And also, our partners or material partners on this have expertise in fatigue, and that really was kind of their recommendation, is to stay in that plus or minus 1% range to get the fatigue life.
Okay, then I will thank you again. Thank you once again for this presentation, Julie. And I would then come to our next speaker, Jaka Tušek. Jaka is an assistant professor at the Faculty of Mechanical Engineering at the University of Ljubljana in Slovenia. Going back to his PhD, he's an expert in designing active regenerators, also on the magnetocaloric side. So he has experience in magnetic refrigeration, but then also won an ERC starting grant, probably the most prestigious European research grant in the field of elastocalorics. And currently, actually, we recently won last year an EIC, that's the European Innovation Council grant, where we now are able to collaborate in the field of elastocaloric. So it's my pleasure to introduce Jaka, and Jaka, it's your turn.
Hello. Can you see me? Can you see me and hear me well?
I can, yes.
Okay, and you can also see my screen, I hope.
Right now,
okay.
we see the Teams.
No, okay.
So
you see the Teams. That's strange.
Yeah, you saw this Teams window in your screen. Yeah.
Let's try again. Entire screen. Yeah, sorry. Okay, now it should work. Is it coming?
Yes. Now it's the let's say your view. It's not the presentation. Yes, now it's in
Okay.
presenter mode. Yes.
Okay,
thanks.
perfect. Thank you. First of all, sorry for a delay. I had some issues with restarting the computer and then updating the Teams. And so thanks, Julie, for stepping up. Okay, so thanks for the introduction and for the invitation, of course. It's my pleasure to be here and to give my talk at this seminar. So the talk will in principle be divided into three parts. I will at the beginning, in the first part, very briefly talk about the motivation behind this work and behind the development of, let's say, new refrigeration technology in general. And also I give really the basics of the elastocaloric effect. Then in the second part, which will be essentially the main part of the talk, I'll give an overview of different segments for which I think they're crucial for the development of efficient, powerful, and fatigue-resistant elastocaloric devices, from elastocaloric materials, loading modes, heat transfer mechanism, operating principles, to geometries of elastocaloric materials, and finally the driving system. While in the third part, I will very briefly present the main results and the development of fatigue-resistant elastocaloric regenerator as a key element of the elastocaloric device, which was built and tested in our lab. So at the beginning, let's just briefly say a couple of words about the motivation behind this work, and in general the motivation behind the development of new cooling technologies. As you can see from this plot, the energy demands for cooling and particularly air conditioning is growing exponentially and is projected to triple in the next 30 years. But our standard cooling and also heat pumping technology called vapor compression technology is old, it's relatively inefficient, and still uses environmentally harmful refrigerants. These refrigerants are no longer ozone-depleting chlorofluorocarbons, which causes significant problems 30 years ago or so, because these were phased out according to the Montreal Protocol and replaced by hydrofluorocarbons, which, as was demonstrated later, has enormous global warming potential. And I really like this example, which clearly shows that if only 1 kilogram of, at that time, most used refrigerant, which was R404A, so if 1 kilogram of this leaks to the environment, and 1 kilogram is roughly the amount that typical air conditioning device have, so this causes the equivalent CO2 emissions compared to driving about 30,000 kilometers with a middle range car. And people are always talking about how driving car is problematic for the environment, but are not talking so much about the refrigerants. So following the Kigali Amendment to the Montreal Protocol, also these refrigerants with enormous global warming potential, which can be several hundred times larger than CO2, they will need to be phased out in the near future and replaced by natural refrigerants only. These are either butane or propane, which are highly flammable and not allowed in larger quantities, or ammonia, which is toxic, or CO2, which has low efficiency in hot climates. So these are some very important limitations of both, conventional refrigerants, such as hydrofluorocarbons, and also natural refrigerants, which causes different, more like safety issues. So these are very serious limitations, and it's really a call for, benign solid-state technologies. And currently, so-called caloric cooling, among which we know magnetocaloric or magnetic refrigeration, electrocaloric, elastocaloric, and barocaloric, this in the recent, 10 to 5 years showed them the most potential for, wide applications and really alternative to vapor compression technologies. So let's now focus on elastocalorics, which show some very promising results in the recent years. So first, let's present briefly the elastocaloric effect, which is the basics of the elastocaloric technology. So the elastocaloric effect is the most pronounced in shape memory materials, which are due to Martesian transformation, which enables due to Martesian transformation two unique properties of shape memory alloys, which are superelasticity and shape memory effect, which are already widely applied in several engineering and also biomedical applications. The elastocaloric effect itself is closely related to the superelasticity of shape memory materials and its latent heat during the transformation. So this stress-induced Martensini transformation is endothermic and exothermic transformation, which causes latent heat release and absorption of the latent heat during reverse transformation. So essentially, all shape memory materials can be considered as potential elastocaloric materials. So this video here shows a basic, let's say, the basics of the elastocaloric effect. So I will show stress-strain response of a typical nickel titanium alloy upon compression. Here is the IR video during the cycle, the temperature time profile, and the temperature entropy diagram, so the thermodynamic cycle that's performed during this cycling. So first step in the cycle is mechanical loading, so material transforms from austenitic to martensitic phase. Because this is done at close to adiabatic conditions, the temperature heats up, the material heats up, and then then it's able to transform this heat to the surroundings, and upon unloading, the reverse transformation occurs, material cools down at the adiabatic conditions, and this cold material is now able to absorb heat from the surroundings. So if we constantly repeating those 4 basic operational steps, we can build a thermodynamic cycle and essentially a cooling device around this, cooling or heating device around this elastocaloric effect. So now this figure shows an overview of different, let's say, segments that are crucial for the development of efficient, powerful, and also fatigue-resistant elastocaloric devices. So in this second part of my talk, I will go through all these 6 segments a bit more in detail, where I will mostly, based on our results, present an overview on the main challenges of these different segments. So obviously, the first thing to talk about are the elastocaloric materials. Since the elastocaloric materials are essentially shape memory materials, we can divide them into a couple of groups, just as in the case of shape memory materials. So we can divide them to nickel titanium based alloys, copper based alloys, iron based alloys, magnetic shape memory alloys with both martensitic and ferromagnetic transitions, and also shape memory polymers. The most widely used, both in terms of superslice shape memory effect, but also elastocaloric effect, is binary nickel titanium alloy, which can have very high adiabatic temperature changes up to 25 kelvins upon loading and unloading, but also requires relatively high stress for the transformation, also has very significant hysteresis, which is a disadvantage. It was, for example, shown that copper-based or magnetic shape memory alloys can have much lower stress required for transformation and lower hysteresis, but also the adiabatic temperature changes are somewhat lower. The story is different in polymers. The background is not Martensini transformation, but rather the reorientation of polymeric chains. Polymers has very low transformation stress required, but also very significant strain. So it might be a bit unpractical that the elastocaloric device requires 6% of strain, but the elastocaloric effect can be quite decent, up to 10 kelvins. The development of new improved elastocaloric materials is a very hot topic in the recent couple of years, as shown in this plot, which shows published papers per year over the last 6 or 7 years, and we can see that a great majority of the papers were produced in the last 5 years. It should be noted that nowadays elastocaloric materials, mainly binary nickel titanium alloy, has not been developed for elastocalorics, but for other applications such as actuators or biomedical applications. So it's not optimized for elastocalorics. So there is significant room for improvement in the development of elastocaloric materials. We have recently performed an overview of different, practically all, we believe, to the best of our knowledge, elastocaloric materials published over the years. And those 2 plots shows the material COP as function of adiabatic temperature changes material, and also stress required to reach these adiabatic temperature changes, again as a function of adiabatic temperature change. So we would like to be very efficient, so we would like to have COP of material as high as possible, but also adiabatic temperature changes, so we would like to be here in this plot, but at the same time we would prefer having lower stress for the transformation. So in that end, we would like to be somewhere somewhere here. So let's talk about a little bit more about the COP of a material. This is a ratio between the latent heat of the transformation, which can be calculated through the adiabatic temperature changes, versus the hysteresis losses at adiabatic conditions. And as such, COP of material presents the maximal possible, the limit up to which the potential device could operate. But in reality, of course, the COP of material, COP of the device, it's much smaller compared to COP of material, because the devices includes other losses as well, such as friction losses, viscous losses, heat transfer irreversibilities, and also the losses related to the enlargement of the temperature span along the device. So unfortunately, the COP of device will be lower than the COP of material. So when people say COP of elastocalorics can be up to 40, they normally talk about the COP of material and don't include other losses in their let's say evaluations. Okay, if we take a look on these plots, we can see that by far the most studied are nickel titanium alloys, which are marked in orange here, both in tension and compression. Well, they are not optimum, neither from the efficiency or from the stress point of view. Based on the literature review, we can see that the most optimal seems to be magnetic shape memory alloys, such as nickel iron gallium or nickel manganese based, or even some doped nickel titanium with copper or iron. But this is purely from the, let's say, from the COP point of view, because these results can be a bit misleading, since most of these materials have not been tested for fatigue, not even a couple of cycles, where unfortunately functional and also structural fatigue prevents the applications of most of these materials in reality in elastocaloric devices. So I would really suggest people who are developing devices, who are developing materials, please perform a couple of cycles on your material, not just one cycle, to see how the performance of this material is after, let's say, these 100 cycles, to see if the response is stable or not. Okay, the next important thing is the loading mode. And in principle, we can distinguish between tension and compression loading. But from the engineering point of view, this means that someone needs to deal with fatigue in case of tension, or with buckling in the case of compression. Both tension and compression has some pros and cons for the elastocaloric technology. The main advantage of tension loading is the ability of applying thin elements, so thin wires or thin sheets with good heat transfer geometry, so with thin walls, large specific heat transfer area, and so on. While the main disadvantage of tension is reduced fatigue life, especially compared to compression. Because in tension, as shown here, any cracks or impurities in the material will already grow and expand during loading, while in compression, those cracks and impurities are getting closed, which can significantly prolong the fatigue life. But the problem is that it's impossible to simply compress thin sheet or thin wire without buckling issues. So it's very challenging to come up with a geometry that can have efficient heat transfer, but at the same time it's buckling. It has buckling resistivity. But fatigue is not the only difference between tension and compression. Julie was showing that before as well. So it's well known that especially in nickel titanium alloys, there's this significant tension compression asymmetry. So in tension, smaller stress is required for the transformation, but larger strain, while in compression, you need larger stress, but smaller strain. However, in both cases, if the transformation is completed, the adiabatic temperature changes of about 25 kelvins can be achieved, but in compression, you need larger stress for that, while in tension, you need larger strain. The difference is also in the homogeneity of the elastocaloric effect over the sample. In tension, the transformation prolongs through Lunder bands, which can be highly inhomogeneous, especially if only partial transformation is applied, while in compression, the transformation can be much more homogeneous, with homogeneous distribution of the temperature, of the adiabatic temperature changes over the sample. So in the recent years, An important part of our work has been focused on studying fatigue and buckling of elastocaloric materials. We have developed a new experimental setup for comprehensive fatigue testing of elastocaloric materials, where the samples are from one side monitored with thermal camera to measure temperature responses, and on the other side with the digital image correlation camera to have to measure the strain distribution over the samples. We have first studied fatigue in nickel titanium tubes in compression, but before we do any characterization, we first perform so-called mechanical stability or training of the material, where in the first 100 of cycles, for example, there is quite significant degradation of the both elastocaloric effect and the elastocaloric effect and superelasticity. But after roughly 100 cycles, the response is stabilized and can be reproducible, which is crucial for elastocaloric devices, obviously. So after training, we then subjected a couple of tubes for fatigue testing, and over the almost entire transformation plateau, all the tubes survived. The tubes were stable enough not to without buckling, and which is precondition, of course, for let's say functional operation. But if they are stable, they don't show any structural fatigue up to 1 million cycles. What was even more important and let's say optimistic is that the functional fatigue there was no functional fatigue either, because when comparing only trained and fatigue tubes, the elastocaloric effect was almost identical, which indicates that after the training, there's no degradation of the elastocaloric effect, which is again crucial for elastocaloric devices. The thing is, of course, the things are much less straightforward in tension. We are currently running a very comprehensive testing of nickel titanium sheets in tension. The idea is to systematically change the mean strain and also the strain amplitudes on the samples, while simultaneously measuring the temperature changes and strain field over the sample. An example of stress-strain response during cyclic is shown in this video, and this sample survived the run out, which was set at 1 million cycles. You can see that there's local strain up to 5% and adiabatic temperature changes up to 7 kelvins, which is quite promising, but only locally. Of course, if the strain is larger, then the total strain is larger, then at some point the sample failed due to the correct propagation as shown here. So based on these results, we are currently constructing a Hayek diagram as shown here. Left-hand side shows pure compression, while right-hand side shows pure tension. And this plot shows the samples that survived with gray and that failed with red. So it didn't reach 1 million cycles. As you can see here, in compression, all the samples when cycled over the almost entire transformation plateau survived 1 million cycles, and they have adiabatic temperature changes up to 25 kelvins. Please note that due to asymmetry, the strain to complete the transformation is lower in compression compared to tension. But while strain amplitude is half of the total strain, right? So again, as shown here, the things are much more complicated in tension, but we are now able to approximate, let's say, the fatigue limit line, which is not straight, but apparently there's an area that corresponds to the middle of the transformation plateau that can have larger strain amplitude compared to other regions. And I think, Julie, you're about to be right, because in this area, the strain amplitude of 1%, which is plus minus 1%, which is total means 2%, actually corresponds to fatigue resistant operation. You can have adiabatic temperature changes up to 8 kelvins, a bit less, most probably, but in this range, which might be enough for some applications. Okay, we are also, since tubes show to be fatigue resistant in compression, we then studied very comprehensively also buckling stability. We tested different tubes with different outer diameters and different inner diameters, and we constructed this, let's say, buckling phase diagram, which shows different buckling modes of different tubes. Here we show slenderness, which is essentially dimensionless length of the tube as function versus diameter to thickness ratio, and we are able now to sort of we detect the different buckling modes. If the tube is thick enough, so the diameter thickness ratio is below 15, and if it's not too long, we observe this interesting buckling unbuckling phenomena. And I have to show that this here, because tube starts to buckle, but then somewhere in the middle of the transformation plateau it straightens back, and the similar thing will occur upon unloading. So this tube actually didn't fail. It also has fatigue resistant operation, and it's thus functionally stable, but it shows this interesting phenomena which is related to asymmetric Martesian transformation in the tube. If the tube would be longer, it would buckle, and if the tube would be thinner, it would buckle locally, so it would sort of collapse into itself. So this is sort of a guideline plot which help us to select the tube dimensions that would show buckling, stable operation in terms of buckling in compression. Okay, so let's go further. So let's talk briefly about the heat transfer mechanism. In principle, we can distinguish between contact and convective heat transfer. So this plot shows two cycles, one for contact and another one for convective heat transfer. In both cases, there are 4 basic operational steps, which is loading and unloading, and in between those steps, it's a heat transfer process. In the case of contact heat transfer, you apply mechanical contact between the elastocaloric material and the heat sink and heat source. This concept is interesting for miniaturization, for example. It can be useful for microcooling because it's somehow limited to rather low absolute cooling or heating powers, and these systems are being developed in Manfred Kohl's group in the Karlsruhe Institute of Technology. On the other hand, convective heat transfer applies macroscopically porous materials like regenerators, through which a heat transfer medium can be pumped in the counterflow direction and can essentially provide larger absolute cooling or heating powers because they contain larger amount of elastocaloric material. Then we can of course distinguish also different operating principles from single stage to multi-stage cycles, such as cascade heat recovery or active regeneration cycle. So this thermodynamic cycles shows basic difference between single stage and active regeneration cycle. In active regeneration cycle, as you can see here, each particle of the elastocaloric material in such a porous structure performs at the right operating conditions, of course, perform its own thermodynamic cycle at slightly different temperatures, which means that you can pump heat at lower temperature compared to ambient temperatures. While in the case of single state cycle, the entire material performs the same thermodynamic cycles, which means you cannot decrease or establish a temperature span over the device, while it can only operate around the surrounding temperature. So for majority of applications, so in this case, in the single state cycle, the temperature span is limited by the adiabatic temperature changes, while multi-state cycles, such as active regeneration cycle, can enlarge the temperature span above the adiabatic temperature changes, which is crucial for most practical applications, which requires a temperature span of 20, 30, or even 40 kelvins. So a couple of years ago, we designed, so almost 10 years ago now, we designed and tested the first active elastocaloric regenerator. And here is here are the 4 basic operational steps and the schematics of such a system. Here in the middle is the elastocaloric regenerator in the form of thin sheets, which are clamped in the grips and then connected to the actuator. And the system is also connected through. It's also connected within the hydraulic system to heatsink and heat source, which are here hot and cold heat exchangers. And we also have a piston pump to pump the fluid and 4 check valves that controls the fluid flow. through this regenerator. So first step is loading, then second step is pumping the fluid through these channels of this elastocaloric regenerator when the material is heated up. Where the fluid is heated up and can then reject heat to the surroundings. The third step is unloading, so material cools down to do the elastocaloric effect, and then we pump the fluid in the counterflow towards cold heat exchanger when this cold fluid is now able to absorb heat from the surroundings. So as I said, a couple of years ago, we designed first of such system. Here is the picture, and here is the IR video of the operation. So there are 4 basic operational steps: loading, fluid flow towards hot side, unloading, and fluid flow towards cold side. And we can see that immediately after a certain number of cycles, a temperature profile is getting established along the length, and we can build a temperature span of 20, in this case 20 kelvins between cold and hot side. So the system works nicely, but due to fatigue, because we exceeded this 2% of strain, it failed after, I think, 7,000 cycles, which is obviously not enough for any practical applications. So now the challenge is to develop a geometry, a proper geometry, as I also mentioned previously. So let's take a look how a geometry of elastocaloric material should look like. So in principle, these are some examples from sheets to wires, which can be used in compression, to tubes in different arrangements, which can be used in compression, to some further more advanced geometries, which can be produced by conventional methods, and hopefully in the future also particularly by additive manufacturing. So some of these geometries has already been applied. Some are currently under consideration by our group and also by other groups. So I believe in the future we can see some of these geometries to be used in next versions of elastocaloric devices. This plot shows our modeling results, where we show cooling power and COP values of the device at 20 kelvins of the temperature span, as function of specific heat transfer area per mass of elastocaloric material at different operating conditions, so different channels for the fluid flow and different operating frequencies. What we can see here is that especially when we work at higher operating frequencies, something like 2 or even 4 Hertz, one should have high specific heat transfer area to reach a better performance. So our system, as I'll show later, has specific heat transfer area of 4.5 square centimeters per gram, which means we are here. So this plot shows an enormous potential of developing more efficient and more advanced geometries with higher specific heat transfer area for the elastocaloric technology. The same goes for the COP, especially if one wants to operate at higher operating frequency, which is the goal, at least reaching frequency between 2 and 4 Hertz. This figure now compares the specific heat transfer area per mass of elastocaloric material versus wall thickness of different potential geometries. So one can quickly see that, of course, the best specific heat transfer area would be in the case of wires and also in the case of plates. But those geometries, especially if you want to use thin elements, can only be applied in tension, which has a fatigue issues, of course. Our tube-based geometry has relatively poor, as I'll show later, heat transfer area, but it could be almost doubled if also the inner surface of the tube would be utilized, which is not, as I'll show later. This plot also shows 2 very nice geometries, or even 3, of the group of Professor Ching-Ping Sung from Hong Kong. They recently designed very nice elastocaloric generators with some very innovative, let's say, geometries for elastocalorics, and they show that it's indeed possible to develop geometries that can show a very high specific heat transfer area and be used in compression. Now let's put on this plot also the geometries we are currently developing, from honeycomb structures to spiral, corrugated sheets, or Hilbert structures. And essentially, those geometries fall on the same line as spiral plate geometry does, because these are essentially the same, let's say, a version of a parallel plate geometry, but they have so-called geometrically induced stability, so they are not flat, but they have curvatures inside, which can improve the buckling stability. So hopefully some of these geometries will be shown to be, let's say, very efficient elastocaloric regenerators to be loaded in compression. Okay, finally, let's talk about driving system, which is, let's say, maybe the most important part of the elastocaloric device, in addition to elastocaloric generator, of course. There are different options. I think Julie talked about this as well a little bit before me. So one can use pneumatic, hydraulic, linear motors, piezoelectric devices, or devices based on screw jack or crankshaft mechanisms, which are essentially driven by electromotor. From the efficiency point of view, the best choice is probably electromotors, which shows efficiency up to or even above 90%. So we have designed an elastocaloric driving system based on a rotary electromotor with a cam disc that loads and unloads 4 phase shifted elastocaloric generators with the goal of work recovery. So as mentioned by Julie, a precondition for efficient elastocaloric device is that the energy that's released during the unloading is efficiently used by direct loading of another antagonistic, let's say, pair regenerator on the other side of the system. So far, the device has only been tested mechanically. So we're using springs here that simulates the elastocaloric regenerators, and this allows us to characterize this system from a mechanical point of view. So this plot shows this characterization. So this is mechanical response of 4 springs, and this plot shows torque over one cycle. And as can be clearly shown, if only one regenerator, or let's say only one spring in this case, is used, the torque fluctuates quite drastically, which is very bad for electromotor point of view. While if we use only two springs at the same time, the torque fluctuates less, but there's still some significant fluctuations. While if we use 4 regenerators, as shown here with the black line, the torque is more or less constant of around 15 Newton meters. We also evaluated the work recovery efficiency. Of course, if there will be no friction, the entire energy that's released would be somehow used by another regenerator. But we have 2 bearings in the systems and very high forces, and this results that only 60% of the energy that's released can be actually used efficiently, which is not yet the goal, but it is a decent value. But we would like to be at 80 or 90%, and we have some ideas how to further improve that in the future. Okay, so I'm almost out of time, I guess, but let me just briefly present our elastocaloric regenerator. It's so-called shell and tube regenerator made of nickel-titanium tubes, which are shown here, and those tubes are supported with support elements along the land, which prevents buckling of the tubes, but at the same time guides a heat transfer fluid in a cross flow around the tubes. Here is the video which shows the operation from the steady state from the initial state up to steady state conditions in a heat pumping mode. So as you can see, the temperature profile is starting to build, and it will reach. Let me try to play it like this. It will reach steady state conditions after a certain amount of time, and let's say the cold side temperature is around 20 degrees, and hot side temperature was about 45 degrees, which means in this case we reached 25 kelvins of the temperature span in the heat pumping mode. Okay, so we tested this device both in heat pumping and cooling mode, where we reached 31.3 kelvins in the heat pumping mode and half of that in the cooling mode. We couldn't go lower because the AF temperature of our material was a bit too high for a cooling device, so we didn't want to go below AF temperature. We had tested this system at different, let's say, mass flow rates and different operating frequencies up to 2 Hertz. And then we tested the system also by adding the cooling or heating power. As you can see here, the device could generate more than 50 watts of heating and cooling power using only 13 grams of nickel titanium, which corresponds to more than 4,000 watts per kilogram of specific cooling and heating power. We evaluated the system also from the efficiency point of view, so from the COP and the exergy efficiency, which is the ratio between the actual COP and Carnot COP, which is the theoretically maximum COP at which the cooling device could operate. We are not yet better than vapor compression, which normally operates with exergy efficiency up to 30%, but we are not that far considering that this is the new technology comparing with the state-of-the-art technology. So we reached the exergy efficiency of around 11%, but there are significant room for improvements, as I have discussed before, particularly in terms of more efficient elastocaloric material and more efficient geometries of the elastocaloric regenerators. So thanks, that's all from my side. This is just a video that demonstrates the operation of the elastocaloric heat pump, where you can see how a heat is actually pumped through the elastocaloric regenerator in this IR image or video. So thank you.
Thank you very much, Jaka, for this very complete overview and very exciting, also showing some new progress already, giving some sneak previews. I would like to open again for questions. So please type your questions into the chat, and I'm happy to read them to the speaker. If there is so far no question from the audience, I would, okay, Osman just congratulating, very good. And then we have a question, yes. For the shell tube EC regenerator, the tubes are seated into the top and bottom plates to secure them in place. There must be a certain seating depth. Could you explain how much seating depth you used for the tubes and what method was used to attach them?
Very good question. We studied that a little bit. Of course, you need some, let's say, how you named it, seating depth, but not that much. Not you would like to have as short as possible because this sort of prevents the heat transfer to the fluid. So we are currently working with let's say the seating depth was, I think, between 2 or 3 millimeters. And the support thickness was also around 3 millimeters. Depending also on the material, because in steel supports required a bit less, while plastic supports would require a bit more, but in this range roughly.
So I was about to ask a question to you, Jaka, and Julie kind of talked about also different modes of mechanical stress besides tension and compression. How would you consider, or have you considered bending or torsion modes also?
Yeah, we are, if I may start, we are thinking about that all the time, essentially. But okay, the problem with bending is that it's essentially tension, at least in some part of material, which would cause failure sooner or later. And also it doesn't really correspond to homogeneous strain and stress distribution over the sample, which is, again, can be disadvantaged depending on how you design the system. A torsion could be much better, especially maybe some multi-axial loading. but it's challenging to design a system because now if you design a regenerator, you need multiple elements, right? And if it's much easier to strain and to compress or using tension on all at the same time. In torsion, you would essentially need to clamp each tube separately, which causes some complexity.
Yes, I agree. Yeah. Are there any other questions? We have used the time extensively that we originally planned, but I think for a good reason. If there's no more questions, I would give it back to the organizer, to Meshat, for the closing remarks.
Thank you, Paul. Thank you very much for hosting the session. Thank you also. I would like to thank both speakers, Julie and Jaka. Very interesting and very nice topic. I really enjoyed all the time. For the people who attended the webinar, I would like also thank you. Later you can see and watch the video of this webinar on the YouTube of the webinar. In case you want to see the video and also see the future webinars, I would ask to follow our LinkedIn group, AM Smart. There we are going to share more information about the future webinars and the other event that we will have in future. Thank you, everyone, and we really enjoyed and have a good time.
Thank you.